Hi everyone, welcome. In this video, we're going to discuss Green's theorem. So the version we're going to be discussing is the circulation or the curl form of Green's theorem. Green's theorem pretty much gives us an alternative way of evaluating line integral of a closed curve as a double integral over the region R that the curve encloses. So here's the statement, the mathematical statement of curl or circulation version of Green's theorem. This is also called the tangential form of Green's theorem, since we have that right here. So what we're really seeing here is that the counterclockwise circulation of a vector field around a simple closed curve, so we're looking at this integral, is equivalent to this double integral over the region R that the curve C encloses of the kth component of the curl. So the kth component of the curl. So the derivation is left out in this video. I'm just going to show you how to work it out in simple example. Another way you can rewrite the right-hand side of this equality, you can also say that to help you remember, this is the double integral over the region R of n sub x minus m sub y. So these are the partial derivatives. So here you're taking the partial of n respect to x minus partial of m respect to y and dA. Now here, the region R that the curve C encloses, it could be any of the type we have discussed earlier with double integral. It could be a type 1 region where you could have curve that looks like this. You could have a closed region like that, so you'll have a top and a bottom. Or it could be a type 2 region. So we know type 2 regions looks like this. So you could have a curve that looks like this. You could have left and right. Or we could have a polar region for R. Polar meaning you can use R theta to describe the region in the XY plane. So it could be something like this or any kind of polar. So we can use R and theta to describe that particular region. So it'll be a polar region. All right, so let's dive into an example. Okay, so here's an example for you. So we are going to use the Green's theorem to find the counterclockwise circulation for the field 3y squared minus 5x squared. That's the ith component plus that. So this is two-dimensional, of course. So our curve C is the triangular region bounded by these curves right here. Okay, so we're going to go ahead and do that. Let's first label our M and N. So M is always the ith component of the field. N is always the jth component of the field. So you might want to identify them first. The next thing you want to do is write down the Green's theorem. So we know the line integral along the counterclockwise oriented curve C of, so there are so many versions of this. You can write F dotted with the unit tangent hat ds, or you can also write this as the line integral along the curve C that's oriented counterclockwise of m dx plus n dy. This is equivalent to, now by Green's, this is the double integral over the region R that our curve C encloses of n sub x minus m sub y dA. So that's the, so we're going to be using this one right here to evaluate this circulation. You could try this or that to find it, and you'll see both answers are equivalent. It's just that doing it as a line integral might take you a little while. But by using double integral, it's actually very simple. So that's what I want to show you. So let's go ahead and compute our partial derivative. So n sub x, so I'm going to take the partial of n, which is this right here, respect to x. So this is a constant. We're only going to differentiate that. So 5x squared, when you take the derivative, you'll get 10x. Then partial of m respect to y. So I'm going to take the partial derivative of m, that's this right here, respect to y. So this is a constant. We're only differentiating this. That will be 6y. All right, so let's hold on to them because they're the components we're going to substitute. So this will go in here and this will go in here. But we need to figure out how the region R looks like, because from that we're going to pick dA, either if it's a type 1 or type 2, or if it's a polar. Most likely this is not a polar region. So let's go ahead and sketch So we're looking at a triangular region bounded by these curves. So let's go ahead and draw that. So here's our XY plane. So y equals 0, that's the x-axis. X equals 3 right here. This is x equals 3 and y equals x. It's right here. Let's suppose that's the line y equals x and y equals 0. Of course, that's all of this, the entire x-axis. So this is our region R. So I'm going to go ahead and just shade that in. So all of that. So sorry, that's going a little over. Let's shade that in. Okay, so this is our region R. So the orientation is this way. We're going counterclockwise. Now let's go ahead and set up. Now this is a type 1 region. So this region right here, this is a type 1 region. So we're going to be doing vertical section like this, summing all of this up over the region R. So our region R is going to be described as set of points in R2 such that so our y is going to go from a function to a function. So the bottom is 0. So y is going to go from 0 to the function x, and x will go from 0 to 3. So that's how you find your bounds on x and y. So if I go ahead and set up my integral, so our circulation for this particular example using Green's theorem, this is the double integral over the region R, m sub x, we know that's 10x, m sub y, that's 6y, dA, and we just fixed how we're going to choose dA. We're going to treat it as a type 1. So this will be the double integral. Our inner integral will go from 0 to x, that's the bound on y right here, and our outer integral is going to go from 0 to 3, and the integrand we have 10x minus 6y dy dx. So we're choosing our dA to be dy dx. All right, now let's continue on. So first we're going to integrate this respect to y. So x is treated as a constant. So let's go ahead and write down the outer integral 0 to 3. We integrate 10x respect to y, you get 10xy minus integrate 6y respect to y, you get 6x squared over 2. So that'll be 3y squared. And we're going to evaluate this from 0 to x. Then we're going to integrate respect to x. All right, so just focus right here. We're only evaluating this first, and then whatever we get, we integrate again respect to x. Okay, so this will be the integral from 0 to 3 of, plug in the upper limit x into each y. So you'll have 10x times x, so that'll be 10x squared. And then 3y, we're replacing it with x, that's 3 minus 3x squared. When you plug in 0, you're going to get 0, so we can just kind of ignore that piece. Okay, so this is what it comes down to. Now here you can combine these guys right here. That's 7x squared. So all of this just comes down to the integral from 0 to 3 of 7x squared dx. And this is a pretty nice integral to do. So we have 7x squared dx. If you integrate that, you'll get 7x to the third over 3. Then you evaluate from 0 to 3. All right, plug in the upper limit. You have 7 times 3 cubed over 3. And the lower limit, you'll get 0. And if you simplify this, you're going to get 7 times 3 squared. That'll be 9. And this will give you 63. Okay, I hope this makes sense. Now, please try it out with as a line integral. So if you were to find circulation by using line integral by any of these versions, you'll have to create 3 different paths. So you'll go along this path, parameterize that, then along this path, and then along this path. So there are 3 different paths to integrate along. And if you sum up those 3 line integrals, you should get the same answer as we got by doing it as a double integral. All right, I hope this helps. So please try it out. I'll see you next time. Take care, everyone.